Is okay.
Yeah.
All right. So the first problem is, as I said, a privacy-related problem where people's data might be requested to, like, you might have to delete it. But model parameters are a function of the entire training set. And so a single user's data could have an influence on the entire model's weights. It's not very trivial to localize the influence of that data point. A second kind of problem could arise. Turns out after all this training, then you realize that you've trained it on some incorrect data. It could be that your annotators made a mistake, or an adversary has manipulated your training set, or that your data wasn't very representative of what your test set is. But retraining a model from scratch is going to be very costly because it was so in the first place. Especially imagine this in the privacy case where people come to you every couple of days. Person one comes, person two comes, and you can't retrain the model from scratch upon every single deletion request. So we would need efficient ways to edit models after you train them. And this is a problem that Unlearning seeks to solve. Machine learning formally is as such. Given that you have a model that is trained on some learning algorithm A on a training dataset S train, the goal is to develop an unlearning operation U that takes this input M, S train, and this set of samples that you want to forget, which is typically termed the forget set. Then you want to return a model M, which is such that the influence of SF is removed while maintaining the rest of the knowledge that M originally had. So it's equivalent to deleting SF from a trained model. We don't tackle this problem for privacy purposes. There is a lot of literature on that. We look at it from a corrective perspective. That is, what if we have manipulations, or what if you train it on some incorrect data? And a very realistic constraint that we use is that you don't always discover all the manipulated samples or all the bad samples because data attribution isn't perfect. So we assume that we might discover a representative subset of it. So let the red samples be all the samples that the adversary has had manipulated, and blue is what the model developer identifies. So you want to remove the influence of all the red samples while discovering only the blue set. Interestingly, here, even if you did retrain from scratch without the blue samples, you would still be retraining your model on all the other bad samples that you didn't discover. So retraining from scratch, as you can see, isn't the gold standard here. Your unlearning algorithm has to do better than that. So the goals of corrective unlearning are twofold. First, which is to improve the accuracy or whatever desiderata you have on the samples from the affected domain distribution, and maintain the rest of the model utility. That is, after unlearning, it shouldn't be that you compromise the rest of the model's usefulness too much because they will still work on the same set of parameters, model parameters. We tackle this problem for graph neural networks, specifically for graphs. Why graphs? Graph structured data is abundant in nature. So graphs are a function of V and E, where V are the nodes, vertices, E edges. So for instance, if you have a social network, your nodes would be the people, and the edges could represent their friendships, citations, or all different kinds of relationships possible between these entities. So before this, I actually worked on connectomics, which is you study the brain as a graph. So you get individual neurons or a cluster of neurons, and you model them as a node, and you get signals from them through a functional MRI machine. And then you learn these different relationships between these nodes. So these edges are inferred in that case. And given that you have a protein structure, you would get a graph of the constituent atoms. You could have a knowledge graph of movies. Bob and Alice have certain kinds of movie preferences. Could you generate a recommendation system for them, given some information about their genre, their preferred genres, what movies they've watched, etc. And we would need to be able to learn over this graph structure data. Graph data is non-IID. Most traditional ML models work on the assumption that your data is independently and identically distributed, but graph data violates that because your two nodes aren't isolated. They have an edge that gives us a lot of information to learn from. And if you discard these edges, you throw away a lot of information. So you want to be able to include these edges, learn meaningful information from that. And GNNs are designed for that. They can learn over non-Euclidean data as well. So a very generic GNN looks like this. So given that you want to learn representations for this yellow node, you would aggregate information from its neighbors as such. You would take all of its neighbors, its first neighbors, and then aggregate them with some function like mean, max, whatever pooling function works best. Put a nonlinearity over it, get the intermediate representations, and do that for how many ever layers are within your GNN. So if you have a 2-layer GNN, you would do this twice for the 2 hop neighborhoods. So finally, the payoff, I guess. Why do we study graph unlearning? So as I said, graph data is non-IID. This can have certain implications. That is, studies have shown that very few adversarial manipulations can greatly affect model performance. And for unlearning, this also means that you also have to tackle the structural effects of these manipulations, because if you poison one node, it could, this due to message passing, as in the previous slide, as you might have seen, the manipulations effects could spread to the other nodes as well, because the other nodes representations are a direct function of this node's features. We employ 2 data poisoning attacks to adversarially evaluate unlearning. The first one is a binary label flip attack, which is also prevalent in the wider unlearning literature, for instance, images. The labels of 50% of the training samples of 2 classes are flipped in our case. So some dogs would be labeled cats and some cats would be labeled dogs. The next one is a more graph-specific attack. This is also a binary attack. Okay. Yeah, so this attack is more graph specific, and this makes use of homophily. That is, GNNs make use of the fact that like wires more often with like. So cats have a lot more incoming, outgoing edges to other cats than cats and dogs. This also means that you could think that it's okay to aggregate features from your neighbors because they are similar. This aggregation isn't very lossy. But what if you spuriously add too many edges between the entities of 2 different classes? Now, this compromises the homophily property of the graph and reduces the GNN's capability to discriminate these 2 classes. And we show that the representations of these 2 classes do indeed collapse together. So it's hard to discriminate cat and dog clusters. So first, we wanted to see, okay, what's the state of the art? We have these attacks. How do methods do? So we used a couple of state-of-the-art graph unlearning methods, and we also took one IID baseline. This method was typically used for images. So we are the first, I guess, work that looks at graph unlearning, but also looks at the wider unlearning methods. Previously, people have just said, hey, we're working on GNNs. There's no way methods for images or text could possibly work here. But as I'll discuss later, this IID baseline actually beats some of the state-of-the-art graph methods at removing the influence of a poisoning attack. So sanity checks are important. For reference, all these unlearning methods are compared to retraining without the SF, that is the set of samples you found to be manipulated, and fine-tuning as a baseline, that is a continued training without SF.
The connection between unlearning and adversarial is not clear to me.
Oh.
These are 2 independent things, or how are you connecting them? Because unlearning, take you are unlearning.
Yes.
Now you are adding an attack. So what's the connection between the 2?
Okay, so the attacks are data poisoning attacks. So pre-training, the data itself is corrupted, and the adversary is separate from the person who is doing the unlearning. So unlearning is done by the model developer after training.
These are 2 separate problems you'll be explaining. We'll have separate experiments on unlearning, separate on adversarial attacks. Or?
No, we just have 2 data poisoning attacks, which we use to evaluate unlearning. So we see that we have these data manipulations, the data, like there's label confusion between, let's say, cats and dogs. We want to see how well, like if a model has been trained on these confusions and it's giving bad predictions over dogs and cats, can we unlearn the influence of these confused labels to restore the accuracy on cat?
What you're saying is there are some points during training, these
Yes.
noisy data points were there.
Correct.
Now, can you unlearn and make sure that they have minimal impact?
Yes.
With a more small scale, large pre-trained model, you can't do this probably, right?
Yeah. So with our compute, we did, so within the graph benchmark data sets, we did choose some pretty large data sets, but they're all after all just benchmark data sets.
Okay.
With our compute, we could only do pre-training over such graphs. Yeah, which is a very real concern for a targeted
What is the
person.
correlation of this? Let's say noise robust learning can also probably do this.
Yeah, so I guess like increasingly people are trying to look at post-training robustness because it's very hard to verify. Well, like there's different aspects to robustness at train time, I guess. One is you would need algorithms that can robustly learn over noisy samples, or sometimes systematically wrong samples. And the second is you would need very clean, high quality data. But as you scale models, you're throwing in a lot of garbage. So you want to shift increasing efforts after train time, because you might not even discover all the bad samples if you subsample the training set.
So you're saying by design, the focus is there.
Yeah, the by design.
Evaluation, I would guess many noise rovers may do reasonably well as well, but
Possibly,
here the
yes.
focus is
On post-training.
post-training.
Yes, yes, yes.
Got it.
Yeah. So as I mentioned before, retraining from scratch isn't the upper bound here. The upper bound we use is unrealizable. It's not an actual unlearning method. It's an oracle that is trained on entirely unmanipulated data. So we had flipped the labels of cats and dogs, right? So this one also has access to all the correct labels of those flipped cats and dogs, which other unlearning methods don't. So for retrain, you just simply remove all the bad samples that you found. So this is as strong as it gets. We saw that these methods were lacking, which we will see in the results. So we designed our method, Cognac. Our method has two components that run in sequence. The first one is a contrastive unlearning component. The second one, ascent descent. These components individually are allowed to repeat for iterations specified by hyperparameter tuning, and the entire algorithm is also allowed to repeat, again, HB tuned. So the first part, contrastive unlearning. This component is entirely unsupervised and works directly on the node representations. So the goal is to push affected nodes towards the representations of their clean neighbors and away from the manipulated nodes. In theory, a manipulated node can at most affect its n-hop neighbors. That's how message passing works. But even this n-hop neighborhood can get really large. So that means that if you assumed every one of these nodes in the n-hop neighborhood was affected, you would have to do expensive contrastive unlearning on all such nodes. But can we somehow reduce the search space? Maybe like on what you do unlearning on. We find that you can do this on just 2 to 10% of the most affected nodes as anchors. We have this very simple heuristic, this no learning heuristic to identify affected nodes. And we get the same performance as using all these n-hop nodes as the affected anchors. So we find that, yes, even though it's like a basic heuristic, the selection works well. So when we choose a very small percentage, like 2 to 10, we see a sharp rise in the performance of the blue line. The blue line represents the accuracy on the affected distribution. So what is the heuristic? So you've found these bad nodes, right? SF. We have one hot encodings for them, so just 1, 0 as the input features. And in our case, we just invert the features. So we just do 1 minus X operation. So if you had a vector 1, 0, 0, 1, it would become 0, 1, 1, 0. And now you do two things. You freeze the original model logits, so you get MX, so the original logit. And then you do a forward pass where just the features of these manipulated nodes are inverted and the rest are kept as is. Then you find a difference between the model's outputs on this inverted feature dataset and the original dataset. So what we're trying to find is, okay, the model, the nodes whose logits were maximally affected could be taken, like you could use this as a proxy for the most affected nodes. It is a heuristic. There are much.
Go to each node, look at its neighbors, and you flip the neighbors labels.
No. We just take the poison nodes. So it's kind of like an intervention study. So what if I change the features of this? Like what if I put up
So you change the features of the node itself.
Yes, manipulated nodes to find its influence in its neighborhood.
Okay, so the node has a feature vector.
Yes.
So that may not be necessarily binary, no, or it is binary in this case.
Yeah,
I won't work on variance much, but yeah, okay, getting the details. So it's a binary set of vectors, so that you can work.
Yes, it's like a bag of words. So it's just a 1, 0 what word exists in the corpus or whatever.
Okay, so that you just invert those and see the impact in the final feature set.
Yes.
Impact is a lot. Then you say that it might potentially
be affected.
node.
Yeah. It's a very simple heuristic. Like we just thought that, okay, maybe this might work, and it does. But there are complex influence functions, but we just thought that, okay, if a simple heuristic works, might as well use it. But it's possible that for other data sets, somebody can just say that, hey, this doesn't work for us. They could use a better influence function if they want to do. It would just be more expensive to identify these nodes that were affected.
So finally, what you look at the output means what? Like the output of GNN is some class labels. So
Yeah, it's the logits.
logits for
Yeah.
you're doing now how many classification? Yeah, the task is classification.
It's a yes.
So it's a per node class label.
Yeah, so a node could be in one of 70 classes in one of the data sets. So you get the logits over all these 70 classes for the original model, the frozen model M, and the MX dash. And you see how much the logits change for each node. The nodes for which the logits are mostly different, as in the class predictions change the most, we take them as the most affected nodes.
It's a general trick. You should not say you should be. It's typically we use this, what loss. So you change some things, but when you look at the impact that the loss is used in like things. So it's a good heuristic.
Yeah. Yeah. I just wanted to be careful that.
So you just slightly pick slightly more only, right? You'll pick up, like, let's say there are 7%, you pick up 10%, that's probably okay.
Yeah.
In your case, that's fine.
Yeah. But it's possible that maybe we are missing something.
Also,
yeah, false negatives. So that's why, like, if somebody wanted to scale it to much bigger foundation models, it's possible that they might find this heuristic to not work. We did ablate it with another method's influence function. Like, they have their own heuristic to find. We found that ours works better.
So larger LLMs, what happens is these days things leak. So so look at the image patch. The background may have information of some other patch because of the attention that the information sort of leaks, which makes it slightly harder. How much leakage happens in GNN kind of graph.
Right.
That's something, yeah, as I said, I don't first-hand experience, I don't have, so I can't tell, but that's the only thing to look at how much information propagates between the nearby things. And I don't think it'll maybe as bad as like these clip-like models in images.
I guess you could think of it as attention. Technically, it's like that you're learning some aggregation over the neighbors.
Yeah.
It's just that in text, you're just looking at the last within the batch. And I don't know much about images, but you just don't have your neighbors could be arbitrary.
So, anyway, yeah.
The next component of our method is ascent descent. DC, like the band. So we perform gradient ascent over the set of manipulated samples that you've found, which just means that instead of propagating the loss, you back propagate the minus of loss. So you're trying to confuse the model, essentially, say that, hey, whatever you're learning is bad. So loss is minus loss on the forget set. And on the remaining data set, we just do gradient descent so that our model doesn't lose our task-specific representations. So this is to make sure the model utility is still good. Now, given that our, I'll get to that later. So we do have some ablations on ACDC as well. The version of ACDC we find that works well for us is where we keep the ascent learning rate to be, we allow it to be lower than descent. Because ascent can destabilize the model and put out too many parameters too much. So one where what we tried is like the ascent learning rate, descent learning rate is the same. One where we allow two different weights for ascent, descent in the same optimization step. To put them both together in one optimization step. What we do is we do losses minus loss, back propagate, and then do descent. So two different steps. We found that this version works the best.
Close to the camera.
Yeah.
That's okay. Yeah.
So given that we have two different seemingly unrelated components, one might ask, hey, do you need both of these? So COGN, which is a contrastive unlearning component, it doesn't really improve the performance too much on the affected distribution over the Poisson model. ACDC is a pretty good baseline. It is not graph specific at all. It's just ascent, descent. You could use this for images, text, whatever. So it's very simple, but it still does perform pretty well. Outperforms most of the graph SOTA baselines.
Yeah, in ML we call gradient reversal is the name
I see.
Commonly used.
Okay.
We use reverse gradients for part of the class and use the normal gradients for rest of the classes.
Right.
Literature, if you see, it will be called gradient reversal. It's a
Oh.
paper from Max Planck a few years ago.
I see. In the unlearning literature is commonly called ascent. I guess so. We just have to go down.
Yes. Okay.
Yeah. What
Gradient reversal.
Yeah, what kind of work is it a part of? Like
Domain generalization or domain adaptation.
I see.
You want to adapt to different domains of data. Then
Right.
you want the features to be domain agnostic rather than not having domain information but having
Right.
information on the content. So for domain you will have reverse gradient.
I
For the content classification you will have
normal
gradient.
Right.
Sort of trick.
I see. Fair
So
enough.
for medical images, you let's say for example have scans from different hospitals.
Mm-hmm.
So you don't want the model to learn the machine specific aspects.
The artifacts of that. Yeah.
Machine. So you'll have like classify which hospital it came from.
Right.
And do a reverse gradient on that it does not use that information at all.
Makes sense.
And the other product you use. So it's again a common. Well, no, it's a neat trick also. It works.
Yeah. It's the most basic thing I guess you could do for any such model adaptation task. Fair enough. So I guess that's the method. That's a high level overview of the method. So coming to the results, I'm going to present it in 3 parts. First, the embedding plots, then the performance on the affected distribution, and then the model utility. To summarize, our method is able to recover the performance of the model when you discover as little as 5% of these manipulations without compromising model utility too much. Most baselines fail to do this even when they're given 100% access to these manipulations. So that's pretty nice. I think even in the outer Unlearning literature, one other method was able to do this for images. It was from Alexandra Printrup's lab, I think. So as you can see in the poisoned baseline, the representations for the 2 classes are completely entangled. You can't discriminate them. Another state-of-the-art method also fails to separate them well, but Cognac does it pretty well, and Oracle is the best case. And you see good, well-formed clusters of the red and blue. Now, this is the performance on the affected distribution. Is it readable?
Yeah.
Okay, cool. So the x-axis is what percentage of the manipulations have you discovered, and the y-axis is the accuracy on this affected distribution. So this maroon line is the poison baseline, and the black line here is the Oracle's performance. The blue line is our method, and red is reaching it from scratch, and rest are the baselines that won't perform pretty well. So almost always our method does perform better than retrain. Occasionally it matches, and sometimes beats the Oracle model, which is kind of really surprising. I don't have a strong hypothesis for that, but it does beat retrain pretty consistently in most of the cases. But that's all good, but you also need to make sure that the rest of your model is useful. So that's where model utility comes in. Cognac doesn't significantly reduce the model utility, but some methods like gin and delete catastrophically compromise this, which also means that your model isn't particularly usable after that. So there is like some unlearning cost because you're working on the same set of parameters, obviously. I would also want to present some interesting findings. These are random random learnings from this project. One is, this is part of our first workshop paper, sanity checks. So as I said, like these people within graph and learning never really looked to the outer literature saying that, hey, these simple methods might not work. Whereas we saw like very simple methods where you just do ascent descent might beat most of the state-of-the-art baselines. Even just fine-tuning beats these other baselines. So that's kind of embarrassing. Also, a lot of these previous baselines, they would use just the overall F1 score of the model to gauge unlearning, which does not really make sense. It would give you no signal. So I guess it was used when they did privacy-oriented unlearning, and the goal was, okay, was the sample recoverable after like MIA? And then did the model performance remain the same? But when you have like poisoning or you have model when you have confusions, that isn't going to give you sufficient signal. So that's where we employed like adversarial evaluations. So that's that. And while unlearning doesn't really assume anything about the data that it wants to forget. So we haven't really characterized what it is that we want to forget. We're just giving the model a set of samples to forget, and you hope that it generalizes well like what the intended behavior is based on the remaining clean samples. But having some knowledge does help. For instance, if you only have label confusions, your features are clean, your overall graph structure is clean. The only thing that's bad is your labels. Some cats are called dogs, some dogs are called cats. The typical practice in graph and learning is to unlink all these nodes, to remove them from the graph so that they don't message pass their bad features, their representations, hidden representations. But as I said, only the labels are bad, right? So what if I just move them to the test set? So you don't compute loss over them. You just allow them to message pass their clean features. And this does increase the performance of our method. The results you saw before were on unlinked because all the other methods do it on unlinked, and we just wanted to be fair. But keeping the links does improve the performance. Thank you.
But if you move to test set performance will go down. It's a wrong label.
Yeah.
So do you evaluate in test set?
No, we don't evaluate on it.
We keep aside basically.
Yeah, so because we have a transductive setting in graph where even the test nodes are actually part of the graph, you just don't compute loss over them.
You'll evaluate on them later.
No.
No, okay.
Okay, so I guess that's imprecise wording. You just don't train on them. You allow them to be in the graph. You allow them to message pass because their features are still clean. The topology is still helpful. It's just that the labels are not helpful. But we do have clean test set.
Okay. So this you don't train on them basically.
Yeah.
Okay.
Yeah. Also, something slightly surprising, confusing might be that when you discover fewer manipulations, your method should be worse, right? Because you have less information to work with. So why isn't the performance on 100% discovery a lot better than 0.25% discovery? So we hypothesize that this also may be because when you unlink a lot of these nodes, you lose out a lot of the structural information. So technically, these what the graph neural network is seeing something that's out of distribution for what it's originally learned, because the representations it has originally computed are a function of the structure as well. But when you remove a lot of the structural information, it's seeing something completely different. So that's another, this ablation also kind of provides some information for that. Limitations and future work. So this work is on benchmark datasets that are primarily homophilic, but future work it will be interesting to see if they work on heterophilic and heterogeneous datasets, including knowledge graphs. We tried our attacks are just two binary attacks. So it doesn't guarantee successful unlearning against arbitrary real-world attacks. And sometimes you can have different kinds of attacks simultaneously. We don't test that either. We have one attack at a time. And it would also be nice to see if Cognac works on images, because even though this unsupervised loss function is used for graph neural networks, I think this triplet loss could be used elsewhere. There is nothing very graph specific. Also, we just do a basic gradient descent over the entire retain set, but can you do something cheaper? Because if your model is really big, even this fine-tuning on the retain set is going to be expensive. Finally, I would like to thank Prof. PK for taking me into his lab in my last year of college, for all the freedom and support to do research that I really loved. Thank you so much for that. My collaborators, friends, and other members of Precog for staying up till 4 a.m. for all the feedback, for all the fun. And my manager at Microsoft Research. I've been fortunate to have really exciting experiences attending iClear, presenting our internship work at iClear. Finally, friends and families for everything academic and not. Yeah, thank you.
Any question?